Okay, here's the model answer for the statistics 2 homework, in which you were given this problem. So you compare 2 different antibiotic treatments, treatment 1 and 2, and you basically measure the number of colonies that grow on these plates. So here are the numbers. That's for treatment 1 and that is for treatment 2. And the first thing that we want to do is we want to calculate the average for the different treatments. So what we do, we can do that very easily in Excel. So what we do is we just put in the equation for that. So it starts with an equal sign and then we put in average. And as soon as we start typing, we come up with some choices. So we just simply click on average and then we drag down. We need to make sure that it is all right. So it is E10 to E12. So we have E10 to E12. And that looks good. So we get 186.67 for treatment 1, and for treatment 2 we just simply drag that over here and we get 243. Right, now for the standard deviation that we want to calculate for these different treatments, we need to be careful, because what we want is really, we want to treat these as samples. They are not of the population standard deviations. They are simply samples of a really huge, almost infinite amount of samples that we could do. So we need to do the sample standard deviation. Now let's calculate that. Equals, and again, as soon as we start typing standard deviation, we come up an S basically, we come up with something like that, and where it says standard deviation dot S. This dot S is important because it stands for sample. So, and again, all we need to do is drag down and see what we get. Again, we have E10 to E12, so these are our samples. Press enter. So that is our standard deviation, 97.21. And we can calculate that for the other treatment as well, and we get 48.69. So very clearly, the standard deviations are very different from each other, and that also means that the variances would be different from each other, and that becomes important when we do the t-test. Now the next thing that we want to do is the standard error that we want to calculate, and to be more specific, the standard error of the mean. Now we need to remember what this actually means, and just let me quickly write something here. We know that the standard error of the mean, SEM, equals the standard deviation that we just calculated here divided by the square root of the number of data that we have in here. So this would be divided by n, and we can write therefore 97.21 divided by the square root of, and we have 3 data points, so divided by 3. So let's quickly calculate that. So we say equals, and we want to take the standard deviation of that and divide it by the square root of 3. And that gives us a standard error of the mean of 56.12, and we can do that very easily for treatment 2. So we've got 26 and 28 for the standard errors. Now what we want to do is we also want to calculate the confidence interval. And again, let's remind ourselves about the confidence interval. And we said the confidence interval, so CI equals the average plus minus the t t factor, t times s over n. And this here, this is nothing else but our standard error that we've done. Now we would get x a bar minus this expression, and that would be our lower limit. And for the upper limit, we would get x bar, that's the average, plus this expression here. So let's quickly do this calculation. So for the lower bound, we said we take the average minus the t factor, and this was given as 4.3 times the standard error, this one here. So that would give us minus 54.66, and we can extend that to treatment 2, so that would be 122.11 for treatment 2. Now let's do the same thing for the upper bound, where we said we take the average plus the t factor, 4.3, times the standard error of the mean. That gives us 428 here. And we do this for treatment 2 as well. So we have basically all the information that we need. Our confidence interval for treatment 1 goes from minus 54.6 to 428. That's the upper bound. And for treatment 2, it goes from 122 to 364. Now, what we want to do next is we want to do a comparison between the two data sets. And for that, we need to formulate our null hypothesis. So let's quickly write down the null hypothesis. And in this case, we can say, right, so the null hypothesis H naught means there is no difference between the means of the two data sets. So x bar A equals x bar B. There's no difference between the two data sets other than caused by sampling error. And we can formulate our alternative hypothesis. And very common is that we say, okay, there is a difference between the two means. So we can write this as x bar A is different to x bar B. And if we use this, this unequal sign, then it means we say the two sample means are different. So two sample means are different. Sample means are different. And because we have this 2 here, we need to choose a two-tailed test. Two-tailed test. If we said we believe that x bar A is, say, bigger than x bar B, or x bar A is smaller than x bar B, so that one is bigger than the other, then we would use a one-tailed test. But the most common approach is that we say they are different, and therefore we use a two-sample test. Now, the test that we want to use for that is a t-test, so it would be we're comparing two samples. The data are not paired. So these samples here have nothing in common with these samples here. So it would be an unpaired test. Unpaired. Now, do these two samples have the same variance? Well, they have very different standard deviations, and we know that the standard deviation is just simply the square root of the variance. So if the standard deviation is different, then the variance must be different here. And we just simply could get the variance by taking both standard deviations by squaring it. So we know that there are different or unequal variances, and we know that it must be a two-tailed test, because we just simply said in our alternative hypothesis we want to go for unequal. So let's quickly do this calculation. So what we do in Excel is we just simply I've messed that up here, so not to worry. We don't really need that at the moment. So what we want to do is we want to do a t-test, so equals. And again, we start typing, so we do t, and we already come up, depending on the settings, with Ttest. Now it asks us for the first array, that's this one here, separated by a comma. Then we do the second array, separated by a comma. And now it asks us for how many tails we want, and we said we want 2 tails, so that would be 2. And lastly, it asks us for the type of t-test. And you can look up in the help section for a 2-sampled unpaired t-test with unequal variance and 2 tails. It has the code 3. And so we are done. So we get a p-value. So let me write this. P-value for this test is 0.44. That's the p-value for this test. Now, what does this test of p-value tell us? Remember, if we have a low p-value, so if we have the p-value is smaller than our confidence or significance level, and this is usually set at 0.05. You can use any other significance level, but commonly it is set as 0.05. If we've got this, the p-value is smaller than 0.05, then our p is low. And remember what I said in the lecture. Let me write this down again. If p is low, h0 must go. So if p is smaller than 0.05, we would reject our null hypothesis. Now, is p lower than 0.05? No. P is 0.44. So if p is high, h0 can stay. So if p is larger than 0.05, then we would accept the null hypothesis. So we would say then that we agree with this statement, and we will probably come to the conclusion that there is no significant difference between the two sample means. The difference that we see here between sample means. The difference that we see here from these data here, or rather from this one here, this difference is only due to sampling error, which we will never be able to get rid of. So I hope this makes sense, and you can see how you can do these calculations in Excel, or even if you have to, you can even do this apart from the t-test, you can do that even by hand if you feel so inclined. Thank you very much for watching, and I hope this makes sense.